Hello. Here we, here we will look at more examples of integer points on parabolas. And this time the modulus, which will be replacing, we will be replacing the parabolas by congruences first, and the modulus will be even. So we'll just start with the same 7x squared. This time I'll take 40y. I'll say take 2 as a free term. Just again integer points on this parabola. Finding them all or determining if there are any, and if there are, finding them all. The criterion for solvability in integers is the following. We take the linear term, the coefficient of it, and reduce modulo it, and then what we have is this congruence. And this is solvable in integers if and only if this is solvable in integers. And that is easy to assess for solvability. So 40 again is a composite modulus. We can break this one congruence into 2, because there are 2 coprime factors inside 40, 8 and 5. So this is the equivalent system equivalent to the single congruence. And 7 is the same as negative 1 modulo 8, so we can cancel it out. Simplifying it into x squared being congruent to just 2 modulo 8. So here, sorry, it's not 8, second time it's 5. And that is not 5, it is negative 2. I apologize. And what can we do? So this is 2 modulo 5, and we can cancel it out, and x squared becomes negative 1, which is the same as 4 modulo 5. So the second congruence obviously is solvable. What is about the first? To assess it, yes, it's good to look at just squares of all possible remainders modulo 8. 0, 1, 2, 3, 4, 5, 6 and 7. So these are possible remainders. Their squares are 0, 1, 4, 9 is congruent to 1, 4 squared is 16, which is 0, and after that 5 is the same as negative 3, so its square is 1, 6 is the same as negative 2, its square is still 4, 7 is negative 1, its square is 1. So we have as squares 0, 2 times, 1, 4 times, and 4, 2 times again. No 2's, non-solvable. So this is non-solvable, so there are no integer solutions for the original parabola, Diophantine parabola. That is it for this equation. Let's now modify it a little bit and hope for the best that we will have integer solutions. So let's replace 2 by, say, negative 23. The story of assessing solvability and eventually of solving is the same. We replace the integer equation by corresponding congruence, and then using the composition structure of the modulus, break single congruence into 2. For the coprime factors of the modulus, this is Chinese remainder theorem. Now for the first, 7 is as good as negative 1. 23 is also negative 1 because it is 24 without 1. And cancelling out this negative 1, we'll have x squared congruent to 1 modulo 8. So that is equivalent to the first congruence. For modulo 5, this is 25 without 2, and this is just 2. So this time x squared, well, it's still congruent to negative 1, which is 4. Right? So that is for modulo 5. And now we do have solutions for both. We have 4 solutions for the first. X modulo 8 is either 1 or 3 or 5 or 7. Well, we can say it quicker. X is odd modulo 8, which is the same as being odd. For the second, we have 2 solutions, and they are plus or minus 2. Combining all possible pairs, we have 8 solutions. So x can be solved in 8 different ways. This found from this congruence, and it looks like we're going to have 8 arithmetic progressions of integer points on our parabola. Let's combine these 4 possibilities for x modulo 8 into just one condition, that x is odd, and hence is of this shape. That is equivalent to the first congruence, or the first 4 congruences. And using this template, we can see when such x has remainders plus or minus 2 modulo 5. And really it's good to do one and then the other will come just by negating of the first solution. So 2 I'm comparing with 1 plus 2l modulo 5. I'm finding l from here, plugging it in there and finding my x. So that is the same as to say that 2l is 1, or 1 is 2l modulo 5. So I need to invert 2, and I can do it by multiplying with 3 both sides. So L is congruent to 3 modulo 5. L is of the shape 3 plus something times 5. So that I can plug in my equation and see what it gives. 1 plus twice 3 plus 5 times something. So that is 1 plus 6, 7, plus a multiple of 10. That is the first arithmetic progression. The second will be when x is negated. So really I'm going to have 8 arithmetic progressions getting glued into 2. And let's now find what y is, say, for this solution, and then we'll write the symmetric solution for negative x. So if x is of the form 7 plus a multiple of 10, how can we see y? So 40y is 23 without 7 x squared. So 23 without 7, and then the square of this. 7 squared plus, what do we have? 7 times 20, yes, and then we have, well, 100 s squared. So that is the square of this, which is x. And now we have to make sure that everything in here is divisible by 40, otherwise we won't find our y. Well, let's look at this term, 23 without 7 cubed. So that is, just write it for my convenience, maybe just 7 times 49. So that is one ingredient, and then we'll combine everything which contains S, and it looks like at least it's not divisible by 40 on the nose, but it is divisible by 20, because I have 20 here and I have, well, 20 as a part of 100, 5 times 20. So what do I have if I then extract with minus sign 20 out of that? We'll have 7 squared S. Well, I can actually extract S as well, and maybe even 7S. So 7 is already factored out. Then 7 times 20 times another 7. So I should have 7 left. And then with the same sign, I'm taking out 20 and 7 is already out, and then S. So that will be 5S. So now I have to do the math here. 7 times 49. Well, I can do 7 times 50, so 7 times 5 is 35. So doing this computation on the side, 23 without 350. Then I have to add 7. So together will give me 30, and then that is really 30 without 350, so that is negative 320. So negative 320 is conveniently divisible by 40. 32 is divisible by 4. The factorization is 40 times negative 8. So that is this bit. And then I have negative 8 times 40. And then I have negative, and then I just have what I have, negative 20, 7s, 7 plus 5s. So to find my y, I have to divide this bit by 40. That will be negative 8, and then I'll 20 by 40 is just 2, but in the denominator. My y has to be an integer. Well, negative 8 is, but this is an integer, because either this or this is even, no matter what. So if s is even, well, I'm happy, I'm cancelling 2 out. If s is odd, then this number has to be even, because we have odd plus odd times odd, which is odd. So that is always an integer. Together with my x, which is given by this template, I have my accompanying y. And that is one arithmetic progression of solutions. And the other one is when x is negative 7, negative 10s, and y is still the same, negative 8, negative 7s times 7 plus 5s all over 2. So that is the second series of solutions. They are all solutions, all possible solutions of this parabola. That's it. See you later.